Hello everyone there. This is Kiran Kumar. Today I am going to give you one important result about comparison based sorting algorithms. Any comparison based sorting algorithm in the worst case takes omega of n log n time or omega of n log n comparisons. That means whatever the algorithm you design in the future too, like even God designs a best algorithm for sorting, especially comparison based sorting, then that sorting takes minimum n log n time in the worst scenario or worst case. Why? We'll see. Before that, I want to tell you what is comparison based sorting algorithm. Comparison based sorting algorithm is a sorting algorithm which takes decisions or which orders the elements based on the comparison of elements, like it compares the elements completely, based on that it decides. There are some algorithms which are non-comparison based algorithms, example radix sort. So radix sort takes elements like 123, 234, it compares the digits, right? It takes least significant digit and it compares, based on that it moves the objects. Okay, then here you are not comparing the objects, we are comparing the digits inside it, right? So they are not comparison based sorting algorithms. Really, comparison based sorting algorithm always compares object versus object, not digit versus digit. You understand that? Then now such comparison based algorithms take minimum n log n time in the worst case. Why? Because the number of comparisons in the worst case are at least n log n. Why? We'll take best algorithm possible and we prove it. Let's say we have God's algorithm. Okay, so for sorting, so this is the best algorithm possible in the world, God's algorithm. Even that God's algorithm cannot do better than n log n. That means it can't do in less time than n log n. Why? We'll see. Let's say God's algorithm also should take the decisions based on the comparisons, right? Let's say this God's algorithm is comparing some two objects first, right? O1 comma O2. Okay. Now I am assuming that I have an objects like this O1, O2, O3, so on, On. Before going to the algorithm, we see how many permutations possible for this n objects. We know that there are n factorial permutations. What I want to say is, if you give input O1, O2, O3 to your God's algorithm, then that God's algorithm is going to decide the right order. But right order is either O1, O2, O3. No one knows it. Based on the algorithm or based on the decisions, it will decide finally, right? Maybe O2, O1, O3. Let me systematically write them. O1, O2, O3. Maybe O1, O3, O2. Otherwise O2, O1, O3. Maybe O2, O3, O1. O3, O1, O2. Then O3, O2, O1. Yeah. Now your sorting algorithm is going to decide the right output. But no one knows the right output. So the right output is one of these 6 permutations. Okay. In general case, if there are n objects, the number of permutations are n factorial, isn't it? Now out of these n factorial permutations, one of them is the right output, but no one knows what is the right output before running the algorithm. Now your God's algorithm is going to decide the right output among that n factorial with some time complexity, with some comparisons. Okay, now I am going to prove that God's algorithm should take minimum n log n comparisons to decide the output. Why? We will see that. Now let's come to such algorithm. Let's say this God's algorithm is going to sort the elements, right? So maybe first time it compares to random elements O1 comma O2, right? After comparing O1 O2, then the outcome possibly O1 greater than O2, otherwise O1 less than O2. My small assumption here is all these objects are distinct, like all are different objects. Not a problem, right? If I take all are distinct. If all the objects are distinct, then if O1 greater than O2, your algorithm is going to take an action, number 1. If O1 less than O2, then your algorithm is going to take action 2. What is that action 1 or action 2? It depends on the algorithm. Finally, that algorithm actions may be moving the elements, right? After that, continuing the process, right? So this action 1 is nothing but doing the remaining work, like sorting the other elements. Maybe action 2 is nothing but a different plan, like how to sort the elements. All these actions should lead to one of the sorted order, right? Okay. Now in this action number 1, probably immediately you will be comparing two more objects, like maybe O2, O3, any random. Now here maybe you are comparing O3 and O4, some two random elements. After comparing O2, O3, then there are two different actions possible. One is, if O2 greater than O3, you do something. O2 less than O3, probably you do something. Similarly here, based on O3, O4, you take two different decisions. What I want to say is, in that way, any algorithm, whatever you write, I can represent your algorithm like a decision tree, right? So based on comparison of O1, O2, you are taking the decision. You are either coming this side or this side. If you come this side, you may compare two other elements. I don't know what are they, depends on your algorithm. Finally, one day, you will reach to a point where this is the last one, like maybe the last comparison, maybe O1 comma ON, I don't know, any two random. So after comparing these two, you decided that the right order is maybe O1, O2, something, some order. Otherwise, you may take another choice like O2, O1, something in that way. Finally, what I want to say is, by continuing this process, you will reach to a point where you get the sorted order, right? That is what the goal of the any sorting order. But now either this is the right order or this is the right order, this is the right order, it will be decided by your action plan. So what kind of control you took, understand? Now example, every time O1 greater than O2, after that if you come here, if to come here, then this is the order. In that way you decide, right? This is the illustration of any sorting algorithm. Now one important point I want to tell you, because there are n factorial possible permutations, we know that, okay, then your output could be anything. Then I want to say that, so these leaves are nothing but outputs, but your output can be anything. Then these leaves are all possible n factorial permutations, isn't it so? Yes. Now your God's algorithm or any algorithm is going to take the right output based on the action plan like this, right? If you understand this, you can understand the proof. Now before going to this proof, I want to ask some questions about this tree. This is a binary tree, isn't it? Yes. Now we are going to find out the worst case comparisons, right? In the worst case, how many comparisons? Let's assume that this tree, because your algorithm is the best algorithm, so that this tree, you made this tree such a way that it is fully balanced. Why I am taking fully balanced, I will tell you. Okay, you have designed your algorithm such a way that that algorithm is creating a tree, just our imagination, but it's fully balanced. Then some students ask why. Then I say, if it is not fully balanced, then the other possible structure is this kind of narrow tree. If your algorithm gets this narrow tree, probably you see every node is about comparison, right? Comparison. At every node you are doing comparison. If you form this kind of lengthy tree, then there are lot of comparisons, right? Then that may not be the best algorithm. If your algorithm is God's algorithm, then that algorithm should not take lot of comparisons, right? It should take as many, as less comparisons as possible. To have as less comparisons as possible, the tree structure should not be like this. Then definitely it should be like this. Let me assume now my tree is like this. Now one fundamental question is, in this kind of tree, if number of leaves are k, you remember, then other nodes also will become approximately k. Okay, then total number of nodes will become 2k. And one more thing, the height of this kind of tree is log of total number of nodes, 2k. So log 2k is asymptotically log k. There is no much difference. Log 2k and log k are same. Now come to this. Then what is the height of this tree? The height of this tree is log of, because this tree is nothing but this one, log of k. K is nothing but number of leaves. Number of leaves in this tree is log of n factorial, where each leaf is one of the possible permutation of n objects. So log n factorial is nothing but n log n. Okay. How this n log n is related to our lower bound, I will tell you. Now, if this is your algorithms, running behavior or flow, then in the worst case, what happens? The number of comparisons we have to calculate, right? See, one comparison here, then in the next level, one more comparison, in the next level, one more comparison. But we know that the number of levels or height of the tree is n log n. Then in the worst case, so you have to go through one, lengthy path, and that lengthy path is nothing but height of the tree. Then I want to say that the number of comparisons are height of the tree, because height and number of comparisons are same, right? In every level you are doing one comparison. Then if your tree height is n log n, then that many comparisons sometimes you should do, right? So maybe sometimes you can escape some of the comparisons, right, but not always, correct? So in some point of time, that means in some cases, maybe you have to go through a lengthier path, correct? Lengthiest path, that is the height of the tree. When you go in this lengthiest path, why? In the worst case anything can happen. Then if you go through that path, then it takes n log n comparison. See, 1 2 3, for every level one comparison. So that's why, so your algorithm, though it is God sorting algorithm, takes n log n comparisons sometimes. That means lower bound for any comparison based algorithm is n log n. That's why it is omega of n log n. No one can do better than this.